Hi everyone, welcome to this lecture. So in this lecture, we will learn about another very important quantity which is used with optimizer. So this quantity is called momentum. So what is momentum? So basically in the previous lecture, we learned about the exponentially moving average. So exponentially moving average is the process to reduce the oscillation in the vertical direction and to increase the speed in the horizontal direction so that we can reach to the minimum value of loss function much early. So momentum means smoothing via weighted average. So when we add a term momentum with the optimization algorithm, it means we are discussing the smoothing via the weighted average. Now, let's see, this is our error surface, or we can see that this is a loss surface. So if you see, the loss is minimum at the middle of this surface. And at the edges or at the outer, everywhere, the loss is very high. So when we have to reduce the loss, basically we have to reach this point, which is our destination. So at the start, we are here. So look at this stochastic gradient descent algorithm. If we see the stochastic gradient descent algorithm, it is vibrating in the vertical direction and it is taking too long in order to reach the minimum or the lower value of the loss function. On the other hand, if we attach a term momentum with stochastic gradient descent, it becomes stochastic gradient descent with momentum. We know that momentum using a weighted average process. So with the help of momentum, what is going on here? It reduces the vertical fluctuation and it increases the horizontal speed. So with the help of momentum, the optimization algorithm reached to the destination, that is the point where the loss or the error value is minimum, very fast as compared to the condition when there is no momentum. So momentum speed up the process or it smoothen the process of updating the weights. Now, how momentum works? Basically, look at this equation. If we see the left side of the equation, this is the exponentially weighted average value of the current time instant, or it is the current weighted average value. This Vt minus 1 is the previous weighted average value. If we see that in order to smooth the previous weighted average value, we attach a parameter beta, and we know from the previous lecture that beta is the parameter which controls the weighted average process. So if we have the previous value of the weighted average and we have to smooth it further, we multiply it with the beta to get the more smooth version. Now, if you see this term, this is another very important term after this plus sign. This is gradient. Now, when we update the weights without momentum, we just use the gradient. But when we have to update the weight with the momentum, we also have to smooth the gradient process. If I multiply 1 minus beta with the gradient term, it is basically the weighted average of the gradient. So you can see the right side of the equation, we are not only smoothing the previous weighted average to get the current, but we are also taking the weighted average of the gradient. Here, theta is the representation of weights and bias, that is both parameters of a deep learning model. Now we have Vt. If we use this Vt, which contains the weighted average process, and if we use this Vt to update the weights, that is theta, then it is called the weight updation with the momentum. So this is now the weight updated equation. So theta are our parameters. That is here theta is representing both weight and bias. So this is the new or updated value of theta, and this is the old value of theta. So in order to update the theta, we have to subtract this quantity from the old value. Here, this symbol is called eta, and here it is used to represent the learning rate. So this eta is a learning rate in this equation. Now, what is Vt? Vt is the current weighted average value. If you remember, at the start of this section, we learn the gradient descent and we update the weight. When we update the weight, we only multiply the gradient with the learning rate to update the weight. But now we are not multiplying only the gradient with the learning rate, but the whole Vt term. So this is the value of Vt term, which contains the weighted average value of the gradient and also the previous weighted average value, which is multiplied by the smoothing factor called beta. So if we use this Vt in the equation of weight and bias updation, then it is called the weight updating method using momentum. So when we use momentum with stochastic gradient, its process become more smooth and more fast. So we can see now again here that when we have the stochastic gradient descent algorithm without the momentum, it has high fluctuation in the horizontal and less speed in the high fluctuation in the vertical and less speed in the horizontal direction. On the other hand, if we add the momentum term with the stochastic gradient descent, we can see that its fluctuation in the vertical direction is less and it speeds up in the horizontal direction. So this is the advantage of adding a momentum to the optimization term. So the purpose of momentum is to speed up the process of optimization. So I hope you understood the concept and the importance of momentum in this lecture. Thanks for listening this lecture, and I will see you in the next lecture.